My friends, we're going to derive the Gibbs free energy equation, this one right here. And to do that, we're going to start off with the second law of thermodynamics, which says the change in entropy of the surroundings plus the change in entropy of the system. If there's no subscript, it means it's for the system, has to be greater than zero. So this is a fundamental equation, the second law of thermodynamics, and we need to make everything in terms of the system because all of these variables are in terms of the system, but here this is in terms of the surroundings. So to make this in terms of the system, we're going to use the thermodynamic definition of entropy, which says that the change in entropy is equal to the energy transferred as heat divided by the temperature. Now, this is true for the system for an idealized reversible process, which doesn't actually happen in real life. But for the surroundings, it does equal the heat transfer of the surroundings divided by temperature. So we're going to make this in terms of the system. And to look at that, imagine we have the surroundings here and the system right here. And if the surroundings lose energy as heat, so we have heat transfer from the surroundings to the system, well, what's lost by the surroundings is gained by the system. So if this is negative Q, then the system has to gain positive Q because we have heat transfer from the surroundings to the system. So we can say that the heat transfer of the surroundings is equal to negative the heat transfer of the system. And no subscript means it's for the system. So we can rewrite this using this equation here. We'll rewrite it below and say that the change in entropy of the surroundings equals negative Q, energy transfer is heat of the system, divided by the temperature. Now there's a requirement here. This is a change in entropy for a process, but there's only one temperature here. So the temperature can't change. So this means we need to have constant temperature for this to occur, constant temperature. Okay, so let's plug this in to our second law equation. So this is our second law, and we're going to bring this down here, and we're going to substitute this change in entropy of the surroundings. So this is now negative Q over T, that's what this one is, plus the change in entropy of the system, which is what we have here, has to be greater than zero. Right on. Okay, so our next step now is to multiply everything. So we'll take this whole equation and we'll multiply it by T. And if we do that, we'll do one step at a time. Negative Q plus T delta S has to be greater than zero. And we have a negative here. And if I go up, see the equation, we have a negative T delta S. So to put the negative here, we could either move this to the other side or we'll multiply by -1. Let's move everything over to the other side just for fun. So we'll subtract T delta S from both sides and we'll add Q to both sides. So that gives us, this is now 0, Q minus T delta S. So we basically reverse the sign for everything here. Now we have Q here and we need this Q to be delta H. So to do that, we use the first law of thermodynamics. The change in internal energy equals the energy transferred as heat plus the work done. This is true for a closed system. Now we'll solve for the energy transferred as heat. So the heat equals the change in internal energy minus the work. Now we need to get enthalpy in here. So to do that, we're going to use the definition of enthalpy. Enthalpy is equal to, or is defined as, the internal energy plus the pressure times the volume. So the change in enthalpy is equal to the change in internal energy plus the change in pressure times volume. Now, if we allow for constant pressure, then this P comes out. It doesn't change, so we can write P delta V right here. Okay, now we're going to solve for delta U and plug it into this equation here. So this is our main equation that we want, and we'll solve for delta U. First, I'll solve for delta U here. So if we solve for delta U, we get delta U equals the change in enthalpy minus P delta V. And now we can sub these two in what delta U is. So Q equals delta U, and delta U is delta H minus P delta V. And that's minus the work. And the work, if we allow only pressure volume work and no other work, no electric work or whatnot, then work is equal to negative P delta V. Remember, pressure is constant, so it's negative P delta V. Work done on the system is positive, work done by the system is negative. So our Q is going to equal delta H minus P delta V minus negative P delta V. Well, this negative and a negative makes a positive, which cancels out with this one right here. So Q equals delta H. And remember, this is constant pressure and PV work only. So we can plug that in to our equation here. This one, I'll write that down here. Q is right here. Q is delta H minus T delta S. And that's literally it. Now we're going to define a new variable or state variable. And G, Gibbs energy, is defined as the enthalpy minus temperature times the entropy. And if we allow for, again, for constant temperature, then our change in Gibbs energy is equal to the change in enthalpy minus temperature times the change in entropy. So if we define this, then that means delta G has to be less than 0 for spontaneity. So this is our equation here that where we see where this derived from, and delta G has to be less than 0 for the reaction to be spontaneous. All right, everyone, hope you enjoyed it. And if you want to see a deeper derivation using calculus, then check out my video on that. See you in the next one. Thanks again. Cheers.